Number 14 does refer to learning you did last year. Proteins are made of amino acids, and proteins are extremely important in biochemistry. Here's an example of an amino acid. You really couldn't understand this last year, but now you can. It's called aspartic acid, and you can see that it is, as drawn here, this is a carboxylate ion. It's a deprotonated form of a carboxylic acid. The words say this is what it looks like at neutral pH. At pH 7, that's neutral, which is most cells exist at around a neutral pH, and therefore most proteins are adapted to a neutral pH. There are certainly many exceptions to this. But let's use this particular example, pH 7. That means the H plus molarity is 10 to the minus 7 molar. You should realize that's a very small concentration of H plus. In such an environment where H plus is very scarce, this negative carboxylate ion has a hard time finding an H plus. There just aren't very many of them in the environment. So this is what it means when it says that amino acids are sensitive to changes in environmental pH. The pH is not always pH 7. And so that's where question A says, how would it change if it were placed in an acidic environment? In an acidic environment, there would be a greater concentration of H+, and that would mean it is likely that this carboxylate ion would bind to an H+. This is an example of Le Chatelier's principle. If there are lots of H+ ions, then the likelihood of binding increases. So at a low pH, this aspartic acid, or this aspartate, would often be found in this red state here, at low pH. This is the common form that you would expect to see. Because the H+ ions are flooding the environment, the likelihood of protonation goes way up. Still in an equilibrium, so at low pH it would look like this, but if you raise the pH, it would go to the deprotonated form. So here you see basic environment. This is what we'd expect to see. Acidic environment, the red form is what we'd expect to see. And that turns out to be a good way of altering a protein's function. Some proteins will not work at a low pH. Other proteins only work at a low pH. You have enzymes in your stomach, for example, that are adapted to working at low pH, and other proteins in your bloodstream, for example, that are adapted to working at a neutral pH. And it's all molecular. It can be explained on the basis of protonation states. This is the chemistry of life.